Okay, so we're going to look at some Chapter 18 problems the same way that we were looking at those problems from Chapter 16 and 17. I'm pulling some questions from the textbook to demo for you, just so you can see examples of how some of these calculations are performed. Okay, so we're going to start here. We have 3 different problems that we're looking at. In each, we're asked to calculate the pH of different buffer solutions. Okay. So we're going to look at the different ways that we can do that. There are 2 methods that you can use to find the pH of buffer solutions, and we can try out both of them, and then you can use whichever one you feel more comfortable with. So for this first example, we're looking at a buffer solution that's 0.2 molar in acetic acid. It tells us that the Ka of acetic acid is 1.8 times 10 to the -5. And it's 0.2 molar in sodium acetate. Okay, so the first thing you have to be aware of is the fact that when we're talking about buffers, we're talking about either a solution that's made up of a weak acid and its conjugate base, or vice versa. A weak base and its conjugate acid. These are the requirements for you to make up a buffer solution. Okay, you're not going to have a buffer solution that's made up of like a strong acid and a strong base. Okay, you need a weak acid and its conjugate, or a weak base and its conjugate. That's what's going to make up your buffer solution. So in the solution that we were given up top, we can easily identify the weak acid portion of this, right? It's the acetic acid. And we have to understand that when we're looking at this sodium acetate, when this breaks up into solution and forms the sodium ion and the acetate ion, that this is our basic ion. So this is going to be the conjugate base of your weak acid. Okay. Remember, we went through all that classification in the last chapter of the pHs of different ions, and this is where that's going to come back into use. Okay, we know that sodium is a neutral cation and acetate is a basic anion. Okay, so this is going to be our weak acid, and this is going to be the conjugate base that makes up our buffer. So we can solve this 2 different ways. Okay, and you're going to see that in the introduction of this chapter. They're going to tell you that you can solve the pH of buffers using an ice table, or you can solve it using the Henderson-Hasselbalch equation. Either way is perfectly acceptable. Okay, if you choose to solve it using the ice table method, you're just going to write out your weak acid equilibrium again, just like we did in the last chapter. Okay, you're going to notice that what's different here, though, is that you don't only have an initial amount of acetic acid. You also have an initial amount of the conjugate base. Because it's going to come directly from that sodium acetate. All right. We can fill in the rest of our ice table the same way. Okay, and we're going to assume, like we've been doing in the past, that when we have a K value that's very small, like this one is, that any X values that are subtracted from or added to our initial amounts are going to be much, much smaller than the amounts that we're starting with. So we can discount them from our calculation. That means that when we set up our K expression for this equilibrium, Ka is going to equal 1.8 times 10 to the negative 5. And that's going to equal 0.200 times X over 0.200. Okay. And that means that our X value is going to equal 1.8 times 10 to the negative 5. Okay. Our X value is equal to our H3O plus, right? We can make little lines to connect them. So that means that by finding X, we found our hydrogen ion concentration. And from here, we can find the pH. We'll take the negative log of 1.8 times 10 to the negative 5. So our pH here is going to be 4.74. So that's how we can solve for the pH using the ice tables. We don't have to use the ice tables though. Instead, we can use this new equation called the Henderson-Hasselbalch Equation. Okay, and actually I'm not going to erase all of this because we're still using the same solution. Okay. So our Henderson-Hasselbalch equation is, which markers? Oops. It's gonna be this. So our pH equals pKa plus the log of the concentration of my base over the concentration of my acid. Okay. We can solve it. We can solve for the pH using this method as well. This method is great. I think you're going to love this because it's a lot quicker. Your pKa value, you're going to calculate from the Ka of your weak acid. The concentration of your base is going to come from the concentration of the sodium acetate, because the sodium acetate contains your conjugate base. And the concentration of your acid comes from the concentration of your weak acid. Okay. You want to know how you calculate a pKa? Same way you might calculate a pH. But when we're calculating the pKa, and I know I talked about this in my last video, we're going to take the negative log of Ka. So when you see this P, you can kind of equate it to the negative log. Okay, so to find the pKa, we're going to take the negative log of Ka. So our pKa value is going to be 4.74. Okay, now we're going to look at our base over acid component. Okay, we have a base concentration of 0.2. Move this up a little bit. My base concentration is 0.200 molar. My acid concentration is also 0.200 molar. So 0.2 divided by 0.2 is going to be 1. The log of 1 is going to be 0. So this whole expression is going to cancel out in this case. So for this particular example, when the concentration of my base is the same as the concentration of my acid, my pH is going to be equal to my pKa. So my pH is going to be 4.74, which is what we found in the last example, so that shouldn't really be a surprise. Okay, so let's look at another example. All right, so for this one, we're going to look at a solution where we have different concentrations of the weak acid and the conjugate base. So now we're going to see what happens when that concentration amount is altered. Okay, so now we have 0.200 molar acetic acid and 0.100 molar sodium acetate. Okay, so again, this is going to be the concentration of our acid. This is going to be the concentration of our base. We want to find the pH of this buffer. We're still looking at an acetic acid solution, so our Ka value is not going to change. And that means that our pKa value isn't going to change. So if we want to use our Henderson-Hasselbalch equation, okay, we already calculated the pKa of acetic acid to be 4.74. So this is going to be 4.74 plus 0.100, because we're going to put the base concentration divided by the acid concentration. Oh, with a little log out front, sorry. Okay, so our pH here is going to be 4.44. All right. Let's try one more example. Here we're looking at the calculation of the pH of a buffer that results from mixing 60 milliliters of 0.250 molar HCHO2 and 15 milliliters of 0.5 molar NaCHO2. Okay, so again, right away, we can recognize that this is going to be our weak acid. And the anion here, the CHO2 minus, is going to be our conjugate base. Okay. Now, to use the Henderson-Hasselbalch equation, we're going to need to figure out what the concentration of the weak acid and the base is in the mixture that we've created here. Okay. So we can't use the molarities that we were given in the question themselves, because once we take these specific samples and we mix them together, and then we have a new volume, a new total volume, their concentrations are going to change, right? When we change the volume of a solution, it's going to alter the concentration. So we have to figure out a new molarity for each one of these first. Okay, So the molarity of our HCHO2, we're going to find by calculating the number of moles we have and dividing it by our total volume. We're going to figure out the moles that we have by taking our molarity and multiplying it by the volume that we added. So our formula for finding the moles from molarity and volume is always going to be a multiplication. And this volume value should always be in liters. Okay. So 0.250 molar times 0.0600 liters. Sorry, that got small, but that says 0.0600 liters. Okay, so we have 0.015 moles of our weak acid. Now to find the molarity of the acid in this mixture, we're going to take that mole value and we're going to divide it by the total volume. Okay, so we have to add these two volume values together to find that total volume. So we have 75 milliliters total. So to find the molarity, we're taking that mole value and we're going to divide it by 0.075 liters. Okay, so even though we were starting out with a solution of our weak acid that was 0.250 molar, once we added in the volume of the sodium acetate, we diluted our acid and now it's down to 0.200 molar. And now we want to do the same process for the base, for the conjugate base. And we're going to focus in again specifically on the basic anion. Okay, so I'm going to call it CHO2 minus because that's the portion of the compound I'm interested in. I don't have to worry about the sodium cation because sodium is neutral. Okay, so I'm going to set up my formula and I'm going to calculate the moles of the salt that I added in here. So I'm going to do my molarity times my volume. So I have 0.0075 moles of my conjugate base. Now I'm going to calculate the molarity. Okay, these are the concentrations of the acid and the conjugate base that are in my current solution. And these are the concentrations that I can plug into that Henderson-Hasselbalch equation. Okay, so my pH is going to be my pKa, which I'm going to get from my Ka value. Let's do that up here right now. So let's take the negative log of 1.8 times 10 to the negative 4. Okay, it's going to be 3.74. Okay, plus the log of the concentration of my base, which is 0.1 molar, over acid, which is 0.200 molar. So now we're going to calculate that out. Okay, we get a pH of 3.44 for this buffer mixture. Okay. Let's look at another set of examples. All right, the next set is some more buffer calculations, and they're asking that we're gonna use both approaches to solve for the pH, the equilibrium approach and the Henderson-Hasselbalch approach. All right, so we'll try both methods to find the pH for each of these buffer solutions. So let's just write down some of this info. I'm gonna shorten benzoic acid to H-benz. Okay, so we're going to start with the benzoic acid. Because I'm going to solve the pH using both methods, I'm just going to find the pKa of this before I get started so I have it for reference later on. So the pKa is going to be the negative log of 6.5 times 10 to the negative 5. And that's 4.19. Okay, and now I'm going to set this up both ways. So I guess I'll solve the Henderson-Hasselbalch first because it's a little shorter. So the pH is going to be the pKa plus the negative log of my base concentration, which is going to come from here, right? The base concentration is going to come from that ionic compound, that salt. So we're going to do 0.150 divided, oh, I didn't mean to write negative log there. 0.150 divided by 0.35 log plus the pKa. Okay, so using the Henderson-Hasselbalch equation, we get 4.67 for the pH. Now we're going to use the equilibrium method or the ice table method. So we'll write out our dissociation for the acid and water. Okay, so we start out with 0.050 and 0.150. Okay, and we're going to assume that these X values that we're subtracting and adding are going to be much smaller than these concentration values that we have here. So we're going to eliminate them from our calculation. And we are going to use the Ka value to solve for X. So Ka is going to equal 0.150 X divided by 0.050. Okay, I'm going to solve for X. And our Ka value again is 6.5 times 10 to the negative 5. Okay, and that X value that we just calculated, that's going to equal the concentration of our hydrogen ion. So we can use the hydrogen ion to calculate our pH. And that's going to equal 4.66. Okay, so both methods are valid for solving for the pH of our buffer. Okay, let's go back to that. The other example they gave us, which was the HCN and the KCN. So here we have 0.250 molar HCN and 0.170 molar KCN. And our HCN has a Ka value of 4.9 times 10 to the negative 10. And again, we'll solve for the pKa right away since we know we're going to need it. Okay. And now we can do our calculations. So Henderson-Hasselbalch, pH equals pKa plus the log of my base, which is going to be my 0.170 molar, over my acid, which is going to be 0.250 molar. Okay, so I get a pH of 9.14 using my Henderson-Hasselbalch method. And let's double check that with our ice table method. Again, we're going to assume that these X values that are being added and subtracted to our initial amounts are small enough that we can cancel them out. Okay, so we're going to rearrange this, or we're going to set up our Ka expression rather. So we have 0.170 times X divided by 0.250, and we're going to solve this for X. So X, which is going to be equal to our H, we'll write H3O plus since we wrote it up there as H3O plus. And that's going to equal our Ka value, which is 4.9 times 10 to the negative 10 times 0.250 divided by 0.170. Okay. Now to find the pH, we're going to use this value as our hydrogen ion concentration. So our pH is going to be the negative log of 7.21 times 10 to the negative 10. And we're going to still get 9.14 back out. Yay. Okay. It's nice when that works out. All right. Let's look at this. This is an interesting one. This is when it starts getting good. So here we have an 89 milliliter buffer solution that contains 0.1 moles of acetic acid and 0.1 moles of sodium acetate. We want to calculate the new pH after adding 0.010 moles of solid sodium hydroxide to the buffer. Okay, so we're going to look at how a buffer changes when we're adding things to it. Okay, and this actually introduces a new table to us that we have to start working with. Okay, it's what I call the BA table. When you're working with these buffer solutions, you have to find a way to keep track of the acid or the base that you're adding to the solution that's going to change the pH of your buffer solution. Okay, and that's what the BA table does. So when you're doing these buffer calculations, you need to start working with two tables now. Okay, table 1 is going to be your BA table. And you have to fill out your BA table first because you're going to use the information from the last row of this table, and then you're going to create an ice table from that. And you're going to use the ice table to find the pH of your solution, just like we've been doing all along. Okay. So here, they're telling us that we have this acetic acid sodium acetate buffer. Okay. So we're going to start by making up a little table to track the changes that are happening here. All right, so we have some acetic acid. Okay, and we're going to be adding sodium hydroxide to it. Okay, and again, this is going to be our BA table. Let's be clear. So we're writing down a representation of what we're about to do when we add the base to our acetic acid. Okay, when we add the base to the acetic acid, we're going to be making water, and we're going to be making our acetate ion. Okay. Now, before the 3 rows on this BA table are going to be labeled as before the addition. Okay, so this is going to be the amount of moles of each thing that are present before we add any sodium hydroxide. Okay, and your BA table is going to have units of moles. That's how we're going to keep track of these things. The second row of your BA table is going to be what you're adding. And the third row is going to be what's left after the addition and after the reaction occurs. Okay. And we can X out that water column again. And this is the row that's important because this is the row that we're going to use to build our ice table after we're done with all this. Okay. So before our addition, we're going to write in the mole values that we got from the problem. So it said that there were 0.1 moles of the acetic acid, and there were 0.1 moles of the sodium acetate. And that's all we were starting with. We weren't starting with any sodium hydroxide. Now, this problem said that we were adding 0.010 moles of solid sodium hydroxide to the buffer. Okay. So we're adding sodium hydroxide to the buffer. In your adding row in this BA table, there should only be one number, and it should be in the same column as the thing that you're adding. What I would like you to use the other two spaces for, though, is to determine whether you're going to be using up your material or creating more of it, because that's going to help you keep track numerically of the changes that are happening. So when you're adding a base, in this case, we're adding sodium hydroxide, that base is going to react with the acid and form more of its conjugate base. Okay, because this hydrogen is going to ionize and then attach to the hydroxide. That means you're forming H2O and acetate. So we're using up this weak acid to form product. So we're going to put a minus sign here because we're going to be using that up. We're going to be forming the acetate when these two things react. So I'm going to put an addition here. Okay. And now we're going to see what's left after the reaction happens. So I started with 0.1 moles of the acetic acid. I'm going to subtract the hydroxide amount from my original acetic acid value because this is the amount of my acetic acid I used up. Okay, hopefully that makes sense. So I'm going to have 0.090 moles left. I am going to look at my acetate ion and I'm going to add the amount of moles of hydroxide to that value. Because when my acetic acid and my hydroxide ion reacted and used up my acetic acid, the reaction that was occurring was the formation of this acetate ion. So as much hydroxide as I added, that's how much acetate I formed. So now I have 0.110 moles of it. And I have no hydroxide ion left. I used it all up. Okay, so now that I have this row, this after the addition row, I need to use this information and put it into an ICE table. But my ICE table needs to be in terms of concentration. Okay, so I'm going to want to go back to that volume value I was given and turn these mole values into concentration values. Okay, so I'm going to move this up a little bit so we can do that. So I had 89 milliliters of solution total. That's what my problem told me. I have 89 milliliters of this buffer. So if I have 0.090 moles of the acetic acid, I'm going to divide that by the volume in liters, and that's going to give me the molarity of acetic acid I have left. Okay, for the acetate ion, it's going to be 0.110 divided by 0.089 liters. And that's going to be a molarity of 1.24. Okay, now these are the concentrations that I'm going to use in my ICE table to figure out what my pH is. Okay, so this is going to now look a lot similar to what I was doing before with the ICE table and using the Ka to figure out what my hydrogen ion concentration is. Okay, so I'm going to erase the top part here, but we want to focus in on these values. Because now we're going to be making our ice table. We finished with the BA table, okay? And we're going to use this last row, this after the addition row, to make up our ice table. So we're going to write out the regular dissociation of our acetic acid here. Okay, and this is going to be our ice table. Okay, my initial concentrations now are going to be 1.011 for my acetic acid and 1.24 for my acetate ion. Okay, and I'm going to fill in my ice table per usual from here. Okay, I'm going to assume these values are small enough that I can cancel them out. So to find my X value, I'm going to use the Ka. Ka for acetic acid is still 1.8 times 10 to the negative 5. And that's going to equal 1.24 times X divided by 1.011. So let's rearrange this and solve for X. Okay, and we get 1.468 times 10 to the negative 5, and that's going to be the concentration of our hydrogen ions. Okay, once we have the concentration of our hydrogen ions, now we can find the pH. And we're going to get a pH of 4.83. Okay. I mean, that's pretty much it. We'll do some more examples of the addition of components to a buffer, but that's going to be your basic process. Just put that frame real quick so you can see most of it. Okay, we're going to try one of these problems again. Same scenario, just looking at a different amount of sodium hydroxide that we're going to add to this buffer. But it's good to get used to the process here. Okay, so this time we have 0.015 moles of NaOH that we're going to add to our buffer. Okay. And we still have that same buffer solution, so it's going to be 89 milliliters of solution with 0.100 moles of the acetic acid, which I think we can shorten out to HAC at this point, and 0.100 moles of sodium acetate. And we're going to focus in specifically on the conjugate base portion of that. right? So if we have sodium acetate, we know that the sodium ion is going to be neutral, so it's not going to take part in any kind of acid-base reaction. But the anion, the acetate anion, is a basic anion, and it's a conjugate base of acetic acid. So these are the two components that are making up this buffer that we're looking at. So in part B of this question, we're looking to calculate the pH after we add a different value of sodium hydroxide to our original buffer. So when you're adding acid or base to your buffer, you're going to want to keep track of that addition using that BA table that we talked about first. Okay, so with your BA table, remember it means before the addition, what the actual addition is, like what you're adding, and then after the addition. Okay, just move this up a little bit. Okay, and you can just write this out. Again, write it out like to mimic kind of what it is you're doing in the reaction itself. So we have acetic acid, and we're going to add this base to it. Okay, so we'll put these two things on the reactant side of the reaction that we write out here, and that's going to produce H2O, which is liquid, and it's going to produce this conjugate base, the AC minus, the acetate ion. Okay, so we're going to keep track of what's being added and subtracted in this BA table. Okay, we can get rid of the H2O section. So before the addition, we're going to go to our initial values of acetic acid and the acetate ion. So we have 0.100 moles of the acetic acid. We have no hydroxide yet because we didn't add any. And we have 0.100 moles of the acetate ion. Okay, now in this case, we're going to be adding 0.015 moles of NaOH. Okay, and we have to ask ourselves, how is this going to react? What is it going to react with? Base is going to react with your acid. Okay, that means that when you're adding the hydroxide, it's going to react with your weak acid, your acetic acid, and that's going to form acetate ion. Okay, so you're going to be using up your acetic acid and you're going to be forming your acetate ion. So we're going to put a minus sign here. You can even write a minus 0.015 if you want. And we're going to be we're going to be creating the acetate ion. So you can either put a plus sign or a plus 0.015 just to keep track for yourself. Okay, so the numerical value comes from the hydroxide that you're adding here. And we just need to be careful of the pluses and minuses. We have to reason these out. So we're using up our acetic acid. That's why there's a minus sign here. We're creating the acetate. That's why there's a plus sign here. Okay, so we just want to see what we're left with. Okay, so we have 0.085 moles of the acetic acid left. We're going to use all of this up, right? So we're not going to have any of the hydroxide left over. And we're going to have 0.115 moles of the acetate ion. And we're going to take these values from our equilibrium row and we're going to turn them immediately into concentration values so that we can put them into our ice table. So the concentration of the acetic acid is going to be 0.085 moles over 0.089 liters. So that's going to be 0.96 molar. And our acetate ion is going to be 0.115 moles over 0.089 liters. Okay. Once you finish that, now you have, wrong thing, circled the wrong thing. Now you have concentration values that you can put into your ice table. Okay. What you can also do at this point, what you should start getting comfortable with, is considering the Henderson-Hasselbalch equation as a way to solve this as well. Okay, as long as we are comfortable that the X is small approximation is a valid approximation, then we can use the Henderson-Hasselbalch equation, because our plus X and minus X that comes out of that ice table isn't going to have an effect on our final value. All right. And a lot of times it's easier to go right into the Henderson-Hasselbalch equation. So let's try that out. We can calculate the pH by using the pKa plus log of base over acid. Our pKa we're going to calculate from the Ka value that was given in the problem. And that's going to be 4.74. Our base is going to be 1.29 molar, and our acid is going to be 0.96 molar. And we get a pH of 4.87 when we add the 0.015 moles of the NaOH. If you wanted to do it using an ice table, that would be totally fine too. Let's do this real quick. So we have our HAC plus H2O. It's going to give us H3O plus and AC minus, and we're going to be calculating the H3O plus value so that we can get a pH from that. Our initial concentrations that we're going to use are going to come from the values that we got out of our BA table here. So we have 0.96 molar acetic acid. We don't need to worry about that. No H3O plus yet, and 1.29 molar AC minus. So then our change is going to be minus X plus X plus X. And our equilibrium is going to be 0.96 minus X, X, and 1.29 plus X. Okay, and we're going to assume that these are small enough that we can disregard them. And then we're going to solve for X using our Ka value. Okay, so Ka is going to equal 1.29x over 0.96. So our X value, which is going to be our H plus value, is going to be Ka, which is 1.8 times 10 to the negative 5, times 0.96 divided by 1.29. So our H plus is going to be 1.34 times 10 to the negative 5. Okay. And then we're going to calculate our pH from that. So pH is going to be negative log of our H plus value. And we see we still get 4.87 back out as our pH. So just showing us again that either method is going to be perfectly acceptable to use to solve for our pH of our buffer, as long as we're confident that that X value that we've crossed out here, as long as we're confident that it's small. And you can always go back and check it the same way that we did in the last chapter, where you'll take this H value, this hydrogen ion value, and you'll divide it by your initial concentration of your acid, and then multiply it by 100. As long as it's below 5%, you're good to go. All right, let's look at one more of these examples. In this case, we have something a little more interesting. I'll just share the screen again to remind you. Okay, we're still looking at that same buffer solution that we have been working with this whole time. But in this case, they're giving us a particular amount of, they're giving us a molarity and a volume of HCl that we're adding to see what the pH change is going to be. So that'll make this a little more interesting. Let's just write this down. So we're going to be adding 10 milliliters of 1.00 molar HCl. All right, let's take a look. Now, what I want you to ask yourself here before we start writing down calculations, compare what we're doing in this step to what we did in the last two steps. We still have our same buffer, but in this case, we're adding an acid to it instead of a base. Okay. When we added sodium hydroxide, that OH minus reacted with our acetic acid, right? So the base we added reacted with the acidic part of our buffer. In this case, we're going to be adding acid. That means in this case, this H plus from the hydrochloric acid is going to be reacting with the basic part of our buffer. All right, and we have to reflect that in the initial reaction we write out for our BA table. So we have the base component, the acetate ion. That's what's going to be reacting with the H plus from the HCl. And it's going to be forming more HAC, which is our acetic acid. Okay, so we can write in our starting amounts of both of them before addition. Okay, we're not going to have any HCl to start with. And now we're going to do the addition section. Right, now they gave us a molarity and a volume here. So what we want to do before we fill in any numbers in our BA table is we want to figure out what the moles of H plus that we have are. So to figure that out, we're going to take the molarity and multiply it by the volume in liters. Okay, so the molarity is 1.00. We're going to take 10 milliliters and divide it by 1,000, 0.0100 liters, which means that we have 0.0100 moles. Okay, and that's going to be the H plus that we're going to be adding to our buffer. Okay, so we're going to have a plus 0.0100 mole right here. Okay, and then again, next step is you're going to ask yourself, well, if my hydrogen ion is reacting with the basic part of my buffer, that means I'm going to be using up this basic part. So that's going to be a subtraction because I'm using it up. So I'm going to lose 0.0100 moles of my base. And as these two things react, I'm going to be forming more of the conjugate acid. So I'm going to be adding 0.0100 moles of my weak acid. So after that addition is over, I'm going to have 0.0900 moles of my acetate ion. I'm going to have none of this acid left over. And I have 0.110 moles of the acetic acid. Okay. We want to find concentrations for our next step. Then you're free to use the concentration values in your Henderson-Hasselbalch equation or in your ice table. Be careful when you're looking at the concentration values because it's going to be moles divided by the total volume. Okay. And our total volume here is changed, unlike in the last two examples. The total volume in this case is the 89 milliliters that we started with, plus the 10 milliliters that we added of the HCl. Okay, so we have 99 milliliters of solution now, or 0.99 liters, 0.099 liters. Okay, so when we are finding these concentrations, a concentration of AC minus, it's going to be moles over total volume. Okay, so 0.0900 moles over 0.099 liters. And for my HAC, okay, so now I can find the pH. I'll just use the Henderson-Hasselbalch equation. It's a little bit faster. So pKa plus log of the base over the acid. Oh, we looked at the pKa a few times already. Forgot it. So the pKa is 4.74. Okay, let's see what our pH is. And we get a pH of 4.65 after this addition of HCl. And if you wanted, you can go back and you could confirm that with by using the ice table. Okay. All right, let's look at our next question, next set of questions. Here we're going to be looking at bases and Kb values. And what we do when we see these Kb values. Okay, so let's just write some of this down. We're going to have a buffer that's 0.50 molar NH3, 0.20 molar NH4Cl. And they're telling us that the pKb for NH3 equals 4.75. Okay, so those will be that'll be the information that doesn't change for our problem here. I'm gonna be able to use that throughout. So our first question here is to figure out what the pH of this buffer solution is. Okay, before we make any changes, we just want to know what the pH of the buffer is. That's going to be part A here. So that's a nice easy one. We can use the Henderson-Hasselbalch equation right off the bat to figure this out. I want you to pay attention though to the formula for the Henderson-Hasselbalch equation here. It's the pH equals the pKa, not the pKb, plus the log of base over acid. I mean, we've been doing that for the last few problems, but sometimes, you write things down without like realizing, okay? So this value here in our Henderson-Hasselbalch equation has to be a pKa value. They gave us a pKb value for ammonia. So in this buffer that we have, our conjugates, we're going to have NH3, and in this NH4Cl that's here, that's where we're going to find the conjugate acid to the NH3, right? It's going to be NH4 plus, because our chloride ion that's attached to the ammonium is a neutral ion. So if the Kb for ammonia is 4.75, then the Ka for the ammonium ion is going to be 14 minus 4.75, or 9.25. Okay, that's how you have to remember. I think we talked about that in the last video I made, even though they didn't discuss it in the textbook yet. But the relationship between your pKa and your pKb, and sorry, these should have little p's in front. The relationship between pKa and pKb is by 14, just like your pH and your pOH. So when you take your pKa and you add your pKb to it, you're going to get 14 back out. Okay? So once you know to do that, now it's going to be pretty straightforward, because you're just going to take that pKa value that you just got, and then we're going to set up our Henderson-Hasselbalch equation the same way. So the log of your base, and your basic component is going to be the ammonia, the NH3, over the acid component, which is going to be the ammonium ion. Right, so the initial pH of this buffer is going to be 9.65. All right. Now we're going to calculate what would happen if we had 0.95 liters of the solution, and then we added 0.01 moles of the solid NaOH to it. Okay, so just a reminder what the question is. And we would expect that when we added the 0.01 moles of sodium hydroxide to this, that our pH would increase a little bit. Okay, that's going to be our expectation. It shouldn't increase dramatically, but it should increase a little bit. Let's just write down the total volume of the solution. 0.95 liters. Okay. So easy enough at this point now. We know that we're going to set up our BA table first to keep track of the addition of the sodium hydroxide. If we're adding the OH minus. You know, again, you have to ask yourself, what is my base going to react with? The base reacts with the acidic component of your buffer. Okay, so it's a really good idea when you're first writing out what your buffer is made of. Like, even if you just write out the two parts of it, it's NH4 and it's NH4 plus, right? And this is going to be your base, and this is going to be your acid, right? They're both weak base, weak acid. But it helps to label them, because then when you're looking over here and you're like, all right, well, I'm adding sodium hydroxide here. If I'm adding a base, the base isn't going to react with the base. The base that I add is going to react with the acid. So that can help guide, you know, how you set up your reaction. So my acid, my NH4 plus, that's what's going to react with this OH minus from the sodium hydroxide that I add. Okay. And one of the hydrogens, one of the little protons here, is going to move over and form some water. And it's going to leave behind the rest of the NH3. Okay, so that's what our reaction is going to look like. Now we can tally up what's going on here. So I'm starting out with, they gave us, we have to do our little mole calculation over here. They gave us molarities and volumes. In this case, they didn't just tell us what the mole values of our buffer components were straight out. So we have to calculate the moles of each one first. So the moles of NH3, we have 0.5 molar times 0.95 liters. So we're going to have 0.475 moles of NH3. We have 0.2 molar NH4 plus. We'll multiply that by 0.95 liters. We have 0.19 moles of NH4 plus. All right, now we have our info for our table. So before I add anything, I'm going to have 0.19 moles of my NH4 plus, no OH minus, water doesn't count, and I'm going to have 0.475 moles of the NH3. Then I'm going to add my 0.010 moles of the OH minus. Okay, and when I do that, like we already indicated in this reaction that we wrote out, the hydroxide is going to react with the ammonium ion and use a little bit of it up and form more NH3. So we are using it up, so we're going to be subtracting 0.010 moles of our NH4 plus, and we're going to be creating 0.010 moles of NH3. Okay. So we're going to have 0.18 moles of the NH4 plus left. We're going to have no hydroxide left. And we're going to have, I can't believe I just used my calculator for that. We have 0.465 moles of the NH. Oh, I'm supposed to be adding that. 0.485. There, I won't doubly embarrass myself. All right. So these are the values. These are my after addition values. So this is what I'm going to focus on now to figure out what my new pH is. Okay. I can use my Henderson-Hasselbach equation to do this. All right. I feel like everyone's going to get real comfortable using that Henderson-Hasselbach equation soon. All right. I'm just going to find concentration values first. You're going to see that you don't have to find You don't have to plug in actual concentration values every time. I'd like to do it because I guess it's in the definition of the formula. You know, it tells you to use the concentration of the base over the concentration of the acid. But we're about to find the concentration values here. I'm about to divide both of these mole values by the same denominator, meaning when I do this division, that denominator would cancel out anyway. So it's kind of an unnecessary step. I'm going to do it anyway because I like to. So the concentration of my NH3 is going to be 0.485 moles over 0.95 liters. And then for my ammonium, 0.18 moles over 0.95 liters. Okay. We already found the pKa from before to be 9.25, so we can use that again. Plus the log of 0.511 over 0.189. Then we're going to do our math out, and we get a new pH, a little bit higher, just like we expected, and it's going to be 9.68. Okay, so it was 9.65, now it's 9.68. And we would expect that little increase by adding just a little bit of that NaOH. All right, now let's see what happens when we add some of the HCl. Okay, here we're doing 30 milliliters of 1 molar HCl to this original buffer solution. Still have a volume of 0.95 liters. Okay. So I guess that we see right away that we're going to need to figure out what this mole value is before we can set up our BA table. So we can do that. I've already calculated the other moles. We can just rewrite them. Moles of our NH3 were 0.475. Because we're going back to the original buffer solution. They're not asking us to keep track of all the changes like in sequence. The moles of our NH4 plus were 0.19. And now we have to figure out what the moles of our HCl is going to be. So we'll do the molarity times the volume. So 1.0 molar times 0.0300 liters is going to be 0.030 moles. Okay, and again, here we have to ask, what is this HCl going to be reacting with? It's an acid, it's going to want to react with the basic component here. So for my BA table, I'm going to be adding H+. That H+ is going to react with the basic part of my buffer, the NH3. And that's going to form some NH4+. All right. So before the addition, I have 0.475 moles. Oh, wrote that in the wrong spot, sorry. I have 0.475 moles of the NH3. And I have 0.19 moles of the NH4+. And I have none of the acid. The addition in this, in this reaction is going to be the addition of 0.030 moles of the H+. Okay. And when I add the hydrogen ion, it's going to react with the NH3 and use it up. So that's going to be a minus 0.030. And as it uses up the NH3, it's going to create more NH4+. So that's going to be plus 0.030. Okay. After the addition is over, I'm going to have none of the H+ left, using it all up. I'm going to have 0.445 moles of my NH3 left. And I'm going to have 0.22 moles of my NH4. Okay. So by my concentrations, concentration of the NH4+. Okay, now I can find my pH. pKa plus the log of my base over my acid. So it's going to be 9.25, same pKa from before, plus the log of 0.468 over 0.232. Okay, so my new pH is going to be 9.55. Okay, and that makes sense. Our initial pH before we added anything was 9.65, right? When we added some hydroxide ion, it crept up to 9.68. But now when we added some HCl, it decreased a little bit to 9.55. But the changes aren't big changes, and that's because we have a buffer solution, and the purpose of a buffer solution is to resist those pH changes. All right. All right, so let's look at the next question. Okay, so for the next question, we're going to look a little bit at some pKa values and relate them to how we would prepare buffers. Share. Okay, so this question asks us which acid would you choose to combine with its sodium salt, right? Because we choose a sodium salt because the sodium ion is neutral. So then the anion would be our conjugate base. And we want to make a solution that has a buffer with a pH of 4.25. So to pick the acid that you would want to use to make this particular buffer, you're going to look for a pKa value that's closest to the pH that you're looking for. Okay, so out of this list here, we have a pK of 1.95, 3.34, 3.74, and 7.54. So the best choice on this list is going to be the formic acid, whose pKa is 3.74, because that's the closest to 4.25. Okay, so it's as easy as that to figure out, which weak acid from a set of weak acids is the best to make a buffer with a specific pH that you're looking for. If we're looking at the same list and we want to figure out which acid we would use to create a buffer with a pH of 7.35, we would do the same process. We look at each one and we see over here we have a pKa value of 7.54. And that means that hypochlorous acid is going to be our best bet for making this buffer. Okay, now the third question is the most interesting one here. And that says, if we have 500 milliliters of 0.1 molar solution of the hypochlorous acid, what mass of the corresponding sodium salt of the conjugate base do we need to make the buffer? Okay, so that question I think sounds a little more complicated than it is. We just have to go back to the Henderson-Hasselbalch equation and let that equation kind of guide us through this question. We know that the pH of our buffer is going to be equal to the pKa plus the log of our base concentration over our acid concentration, right? We also know certain things from this question. We know that the pH that we're looking for is 7.35. We know that the pKa of the hypochlorous acid is 7.54. And we know that the concentration of the weak acid component is 0.10. All right, so we can solve this equation and we can find the concentration of the base. Once we have the concentration of the base, we can figure out the moles of the base. We can figure out, once we have the moles of the base, we can figure out what the mass of the salt is. Okay, but it's going to start here with us solving out for the concentration of the base. So let's subtract the 754 from both sides. So we get negative 0.19 equals log of our base over 0.10. Okay, and we have to get rid of this log. So to do that, we're going to raise both sides to the 10. So that'll cancel out. So we end up with 0.646 equals the concentration of the base over 0.10. So then we'll multiply both sides by 0.10. And we get 0.0646 is the concentration of our base. Okay, so step one, done. We found our concentration. Now we want to figure out what the mole value of our base is. Okay, moles is going to be the molarity times the volume. Well, we just found the molarity, right? Put a little m there. So the molarity is going to be 0.0646. The volume is that 500 milliliters that we were told in the beginning of the problem. So we'll turn that into liters. And the moles of our base is going to be 0.03228. Okay, so this is the moles of our base. And our base in this case is ClO minus. Now they want to know what the mass of the sodium salt is that you would need to add to get this amount of base back out. Okay, so look at the formula for the sodium salt of this. If I wanted to make the sodium salt of the hypochlorite ion, I'm going to add Na plus to it. Okay, so this is the sodium salt. And when you put this into solution, it's going to break up into sodium ions, which we don't care about because they're neutral. And then the ClO minus ions, which we do care about because that's the conjugate base for the hypochlorous acid. Okay. But we see that this is a 1-to-1 ratio between the sodium and the hypochlorite ion. So if we know the moles of the ClO minus, we know the moles of the sodium. We also know the moles of the sodium hypochlorite. Okay. So if we look up the molar mass of this, let's do that real quick. It's 74.44 grams per mole. Now we can figure out the mass of the sodium hypochlorite that we would need to create the buffer with the pH that we're looking for. Okay, so we have 0.03228 moles. In 1 mole, there are 74.44 grams. So we would need to add 2.4 grams of the NaClO to the 500 milliliters in order to have the correct concentration of the anion here to get a pH of 7.35 for our buffer. Oh, car alarm. All right, the next question, we're going to look at the titration process. Right, we've been talking about making buffers before this. Now we're going to be talking about a titration. This is when we have one solution whose concentration that we know. In this case, that's the sodium hydroxide. And we're going to use it so that we can titrate the solution we don't know. And we're going to calculate the pH. Okay. And I say we don't know in this case. I mean, we have both of the molarities in this case. It's not like we have an actual unknown acid or base. Our unknown here is going to be our pH at these different points in the titration process. So it's going to be a little bit different than what you did in lab in terms of the calculations that you're doing. But the process is still the same if you want to like imagine it. If you want to imagine the titration process. It's still going to be a lot like what you saw in that video. So we're just going to calculate the pH of these different points. We're going to see what the pH would be after we add 30 milliliters of the nitric acid. We want to see what the pH would be at the equivalence point and after the addition of 60 milliliters of the nitric acid. It also might be a good idea just to have a baseline to calculate what the initial pH of the solution is as well. Then we can say, like, it's going to go up and down from that initial value. So even though they're not asking us to calculate the initial pH, we can still do that. I'm going to write down the info for our titration. Okay. So we have a 50 milliliter sample of the sodium hydroxide that we're starting with. So if we wanted to calculate the initial pH here, we're going to be looking at the concentration of the hydroxide ions to help us do that, right? So we know that the concentration of the OH minus is going to be 0.200. And we know we can calculate the POH from that. Okay, now I'm going to calculate the pH from the POH. So we have an initial pH of 13.3. And again, I'm just doing this so that we have a baseline to compare the rest of our pH values to. It's not like necessary because I didn't ask for it. Okay, so our first calculation is going to be what the pH is after we add 30 milliliters of the nitric acid. Okay, so strong acid and strong base titrations are different than your weak acids and your weak bases because of the fact, that you're not going to be seeing any Ka or Kb values as part of your calculations. Once you know the concentration of the hydrogen ion or the hydroxide ion when you're doing a strong acid and a strong base titration, you're going to be able to do a pH calculation directly from that. Okay, so there's no like Henderson-Hasselbalch step for a strong acid and a strong base titration. There's no ice table even that you need for a strong acid and a strong base titration. The only thing that you need to do is maybe set up a bar table for yourself so that you can keep track of how many moles of the acid and or base, whatever, that you used up. Okay. So this is going to represent the reaction that's happening between the HNO3 and the NaOH. And we want mole values to put in here, right? So we know that we had 50 milliliters of 0.2 molar NaOH. So to find our our moles of OH minus, we're going to take that molarity and multiply it by the volume in liters. Okay. When we're going to do the same thing for the HNO3 because we're adding the 30 mils there. So we have 0.2 molar. That's not right. Okay. Must have had something else in my calculator as well. I'm like, that's not right. So we're going to take the molarity of the HNO3. We're going to multiply it by the volume of 0.030 liters. So 0.2 times 0.03. Okay. We can use these mole values now to figure out, what we have left over. So in this case, before our addition, the only thing that we're going to have here is our hydroxide ion, okay, because we had an NaOH solution. So we're starting out with 0.0100 moles of the hydroxide ion, and we don't have any H plus left. I'm sorry, we don't have any H plus yet. And we're not going to really keep track of the water because we don't have to worry about what's happening in the water column. In the addition step, we're going to be adding 0.006 moles of the H plus okay? And if we're adding the H plus, that means that that's the amount of OH minus that we're going to be using up so that it can react with this H plus. So we could think about this as using up the OH minus. Okay, so there's more hydroxide than hydrogen ion here. That means that all of our H plus is going to get used up in this process, and we're going to have none left. And we're going to have 0.004 moles of the OH minus left over. All right. Now, because we're working with a strong acid and a strong base, once we have the moles of the hydroxide ion, we can turn this directly into a concentration value. And once we know the concentration of OH, we can use that to find the POH and then the pH. Okay. This is why it's great to work with strong acids and strong bases, because we can find those pH values directly from the hydroxide ion or hydrogen ion concentration. So we'll start with the concentration of OH minus. That's going to be our mole value. And we have to divide it by the total volume of our solution. Now remember, we started with 0.0500 liters, and then we added another 30 milliliters to it. Okay, so we have to take both of those volumes into account to make up our total volume. Okay, so that's the NaOH volume plus the HNO3 volume. Okay, and we get a molarity of 0.05 molar. Okay, from that concentration value, we can find the POH, the negative log of 0.050. The POH is going to be 1.30. So then to find the pH, 14 minus 1.30. Our pH is going to be 12.70 after we add that nitric acid. Okay. So that's easy enough, not too bad. The second part of this question asks us, find the pH at the equivalence point. Okay. Now this type of question is not even worth a calculation here, right? Because at equivalence, when you're working with a strong acid and a strong base titration, the pH is always going to be 7. And think about why this is. Regardless of the strong acid or the strong base that you're working with. So we're putting examples down, but this could be representative of any strong acid and a strong base. Okay. When this reacts, your H plus and your OH minus are going to form water. And you're going to be left with sodium ions and chloride ions, right? And a strong acid and a strong base, these ions that were part of your strong acid and your strong base, they're both neutral ions. Okay, so there's nothing in this product side of this reaction that has any pH value associated with it. Well, that's not true. It's a pH of 7 because it's neutral, but it doesn't have a particular acidic or basic component associated with it. So when you're at the equivalence point of a strong acid, strong base titration, there's going to be no pH contributor there. You're going to just have a pH of 7. It's going to be neutral. That's not true when you have a weak acid or a weak base that you're titrating with, because a weak acid is always going to have a conjugate base. And same thing for a weak base, it'll always have a conjugate acid. But for a strong acid and a strong base, their counter ions are going to be neutral. So for the third calculation here, we're going to look at the pH after the addition of 60 milliliters of the HNO3. Okay, so the amount of our HNO3 has increased dramatically here. We want to see what the new pH would be. Okay, so we're going to need our mole values again. We already calculated the moles of our OH minus that we're starting with. 0.0100. And in this case, we want to see moles that we would be adding with 60 milliliters instead of 30. So we'll take the molarity of the HNO3, multiply it by the volume here in liters. Okay, and now we're going to set up our little bar table in the same type of way. We had H plus OH minus H2O. So before the addition of anything, the only thing that we had was the hydroxide ion, and we had 0.0100 moles of it. Okay. Now we're going to be adding the 0.012 moles of the H plus. And now you have to ask yourself, and this is a very important connection that we have to make here. You have to look at these two values. You have to say, right, which of these values is larger? And in this case, our acid value is larger. That means that I have more acid present than base. So when these two things react, I'm going to end up using up all of my hydroxide. Okay. Gone. It also means that that's how much acid I'm going to end up reacting. And I'm going to have leftover hydrogen ions and no leftover hydroxide ions, because I added more hydrogen ions than the hydroxide ions I already had. Okay, so we have 0.012 minus 0.01. And we have, after the addition of our hydrogen ion, we have 0.002 moles of H plus left. And we have no hydroxide left. So this is what's going to determine our pH now. Okay, we have to find the concentration of our H plus ions. So to do this, we'll take the moles that we have left over, and we're going to divide it by the total volume, which again, we had 50 mils here, and we had 60 mils here. All right, so we're going to add that together, 110 milliliters, or 0.110 liters. Okay. Now we can take the pH directly from this hydrogen ion concentration value. It'll be the negative log of 0.0182. So our pH is going to be 1.74. Okay. So you see how that switched dramatically. As soon as we used up all the hydroxide ion that was present, now our pH is going to be determined by hydrogen ions instead. So the pH that we get is a much lower pH value. So now we're going to look at a weak acid strong base titration, and we're going to see kind of how different this is. Okay. The strong acid and strong base titrations are very straightforward. You know, there's no Kas involved or anything like that. You're just looking for the concentration of hydrogen ions or hydroxide ions. There's a little more to do when we are working with weak acids or weak bases. Now, there are 5 questions that we're going to be looking at here, and we're going to calculate these individually. Okay. Maybe except C and D we'll kind of do together. All right, so we're looking at a 40 milliliter sample. It's 18.7. We're looking at a 40 mil sample. And we're titrating it with 0.2 molar KOH. Okay. The other thing that you have to remind yourself of when you're doing titrations is, you know, the process that's being described. Like, you know, think about like what's being asked of you and about what the procedure is that you're supposed to be undertaking to do these calculations. So here they're telling you that you have a 40 milliliter sample of this nitrous acid. That's what you're starting with. All right. So if they wanted to know what like your initial pH was for this titration, you're just going to be focusing on what you're starting with here, your 0.1 molar nitrous acid. Now, you're going to be adding the KOH to the nitrous acid in small amounts. Okay. And we've picked the points that we're going to look at the pH of the solution. All right. But you have to remember that we're starting with like a flask of nitrous acid and we're adding the potassium hydroxide to that. So the first point in the titration that we're going to be focused on is the pH after we add 5 milliliters of KOH to our solution. Okay. And we would expect that as we add the KOH to the solution, we're going to slowly be increasing the pH of the solution, right? So hopefully that makes sense. But to do this, we need to keep track of the additions that we're making, and we're going to do that in a BOT table, right? We need mole values for our BOT table, so let's just calculate the mole value for for both of them, okay? So for our HNO2, molarity times volume, Okay. And when you see this KOH, the strong base that you're adding, again, remember that this is going to be equal to the OH minus, the value that or the base component that you're adding to the titration. So you're not really worried about the neutral potassium cation. You're going to be focused on that hydroxide ion and how that's going to be reacting with your weak acid. Okay, so let's look at the reaction that occurs here. We have our HNO2, and we're going to be adding some base to that. We assume that we're going to be forming water. And when that hydrogen ion moves to combine with the hydroxide ion, it's going to leave behind the nitrite ion. Okay. So before any addition, all we have is going to be our HNO2, right? So we're going to have 0.004 moles of our HNO2. And we're not going to have any hydroxide ion. Water doesn't matter. And we're not going to have any nitrite ion. Okay. Now we're going to focus on this addition row. We're going to be adding 0.001 moles of the hydroxide ion. Okay. And when we do this, we're going to be reacting it with the nitrous acid. Okay. So we'll put a subtraction there. And we're going to be creating the nitrite ion. So we'll put a plus sign over here. Okay. So after the addition, keeping track of what's going to be present after we add this hydroxide ion, we're going to have 0.004 minus 0.001. That's how much of the nitrous acid we'll have left. And we're going to be creating 0.001 moles of the NO2 minus. Okay. During this process, we've used up all the hydroxide ions. So we have none of that left. All right. Now, if we look at what we have left over in this addition row, we can use this, again, we can use this to put into an ice table, or we can recognize that what we have here is a weak acid. What we have here is a weak base. And when we have our weak acid and our weak base, we can use our Henderson-Hasselbalch equation to figure out what the pH is of the solution. All right. I'm just gonna show you guys that it's okay to use the mole values here. Like I know we talked about it before, and I pretty consistently, I mean, you guys will see this when if you work with me in class or in tutoring or whatever, that I'll consistently change these values to concentration just because it makes me happy to do so. But you don't have to. It's not a requirement when the volume of each is the same. Okay. So our Henderson-Hasselbalch equation is pH equals pKa plus the log of your base over the log of your acid. We have an HNO2 Ka of 4.57 times 10 to the negative 4. So let's find the pKa of that real quick. So we'll take the negative log of the Ka value. And we get 3.34. So we have 0.001. That's our base over 0.003. That's going to be our acid. So we end up with the pH value of 2.86 after we added 5 milliliters of the potassium hydroxide. Okay, so hopefully that makes sense. All right, let's look at the next question. The next part of this asked us to find the pH at 1/2 the equivalence point. All right, 1/2 the equivalence point. This is a titration point that you want to be kind of familiar with. Okay, and we're going to look and see. Sorry, I had to roll up my sleeves. We're going to look and we're going to see why in a second. Okay, so I erase the things that we don't really need anymore. The definition of 1/2 equivalence point is going to be the point in your titration where, in this titration anyway, where the amount of base that you add is going to be 1/2 the initial amount of the acid. Okay, that's half equivalence. If the equivalence point of a titration means that your moles of your base is equal to the moles of your acid and vice versa, then the half equivalence point is when the moles of the thing that you're adding is equal to half the initial amount of what you had, what you started with. So in this case, when we add enough moles of hydroxide ion so that it's half the mole value of the nitrous acid that we started with. Okay, so our initial amount of HNO2 is 0.00400 moles. So at 1/2 equivalence, our OH minus moles is going to be 1/2 that value, 0.00200. Okay. So now let's see what happens when we put this into a Ba table. We have our HNO2. We're adding our OH minus to it. And we're forming our H2O and our NO2 minus. Okay, so we started out with 0.004 moles. And we're adding 0.00200 moles of OH minus. Okay, so what's going to happen? We're going to use up some of the HNO2. And when we do that, we're going to be left with 0.004 minus 0.002 moles of our nitrous acid. We're going to use up all of our hydroxide ion. There won't be any of that left over. Water doesn't have to worry about. And as we are using up our HNO2, we're going to be creating the conjugate. Okay, so we're going to be creating this much of our conjugate. Okay, now what I want you to notice here is that this mole value of your weak acid is the same as the mole value of your weak base. Okay, and that's important because when you go to now put this into your Henderson-Hasselbalch equation to solve for the pH, what happens when you have the same weak acid and weak base values? Our pKa doesn't change, it's still 3.34. But we're going to have the log of 0.002 over 0.002. This is going to be the log of 1. The log of 1 is 0. So at half equivalence, your pH is going to be equal to your pKa because the moles of your weak acid and the moles of your weak base are going to be the same value. Okay, so let's take a minute and write that down. At half equivalence, your pH will equal your pKa in a weak acid strong base titration or in a weak base strong acid titration. Okay, and that's because you're going to have exactly equal amounts of your weak acid and its conjugate base here. All right, so now we're going to look at parts C and D, which are asking us about the equivalence point here. And we're going to think about the equivalence point. We're going to use the same type of thinking that we did for this half equivalence point to tackle the equivalence point. Okay. We know what the definition of equivalence point. Equivalence point means that the moles of our acid are going to equal the moles of our base. Okay, that's going to be our our simplest definition of what equivalence point can mean. So we know that at the equivalence point, these two things are going to be equal. All right, so we've already calculated the amount of moles of our weak acid that we have in our solution. That means that we know that at equivalence, we have to have the same mole value of KOH, right? So at equivalence, the moles of our hydroxide ion has to equal 0.00400 moles because that's how many moles of HNO2 we're starting with. Okay, so they asked us what volume is required to reach the equivalence point. Well, molarity is going to be moles divided by liters, right? So if I know the molarity of my KOH, which I do, and I know the moles of my KOH, which I just found out, I can figure out what volume of KOH that's going to represent. Okay, so let's rearrange our molarity expression and solve it for liters. And then we can plug in the stuff that we know. So it's going to be 0.004 moles divided by 0.200 molar. Okay, and we get 0.02 liters of KOH would need to be added to reach the equivalence point. Okay. So that means that if I had 40 milliliters of 0.1 molar nitrous acid in a flask, and I was titrating it with 0.2 molar potassium hydroxide, I would have to add exactly 20 milliliters or 0.02 liters of the potassium hydroxide to the nitrous acid before I reached the equivalence point. As soon as I added 20 milliliters or 0.02 liters, at that point, the moles of my H plus would be equal to the moles of my OH minus. Okay, so at equivalence, let's just put a little thing here. We have 0.0200 liters of KOH. Okay, our next calculation is to find the equivalence point pH here. Okay, and let's take a look at what happens. Okay, so we're going to write out our BA table here. Have our H and O2. We're going to be adding our OH minus to it. Okay, and we have to track what happens now that we are at equivalence. Our before value is going to be 0.004 moles for our H and O2. Okay, and our addition here, this is definitely something that's a little bit different. Our addition in this case is going to be, we're at equivalence, so we know that the moles of hydroxide that we're adding is going to be the exact same amount that as the acid that we already had. Okay, and you see what happens at equivalence, right? These two things are going to react together. And there's exactly the same amount of each one. That means that after the reaction happens, I'm going to have exactly no HNO2 left over, and I'm going to have no OH minus left over. The only thing I'm going to have left is going to be the conjugate base that was produced while these two things were reacting. Okay, so 0.004 moles of each reactant were consumed and 0.004 moles of the nitrite ion were formed. Okay, so this looks a lot different. This BA table looks a lot different than the ones that we worked before. Okay, but what ends up happening is that this nitrite ion, which is the only thing left after the nitrous acid and the hydroxide are done reacting, this is going to enter into its own equilibrium reaction. Okay, so we need to use this mole value of the nitrite ion that's left, and we are going to put it into an ice table. And we're going to use that ice table to eventually find the pH. Okay. Now we know that to put something in an ice table, we need a concentration value. So to find the concentration of the NO2 minus, we're going to take this mole value that we found, and we have to divide it by the total volume. I'm going to just write that here so we remember that this is going to be the total volume. So that's the volume of the HNO2 and the volume of the KOH. Okay, and that's why they had us go through that step right before this where we found the volume of the KOH at the equivalence point, because if we didn't, we would have to do it anyway right at this point. Okay, so we know that the volume of our HNO2 is 40 milliliters and the volume of our KOH is 20. Okay, so our total volume is going to be us adding these two values together. So to find the concentration of our NO2 minus, it's going to be 0.004 moles over 0.060 liters. And we get a concentration of 0.067 molar. So this is the concentration of our nitrite ion. And this is the concentration that we're going to put into the ice table that we're going to form. Okay, so I'm going to erase the BA table because we don't need it anymore. Now we need to make an ice table. All right, now before we start filling in our ice table, you know, it's best to write out the reaction that's going to be occurring in water first. And in this case, we're focusing in on this nitrite ion. We're looking at the reaction of the nitrite ion with water. Okay. So it's going to act like a standard base does, and it's going to pull one of these hydrogen ions over to itself, and it's going to leave behind a hydroxide ion. Okay. So this is all going to be pretty standard now. The initial concentration of our nitrite ion is going to be 0.067. And we're going to fill in the rest. We usually do. Okay. And now we're left with the step where we need to find our X value. And in this case, our X value is hydroxide. And we're going to do that using our Kb value, right? Hydroxide ion in the products means that we need to use a Kb value to solve for the equilibrium. We were given a Ka value initially, but we can find our Kb value from this. So let's do that calculation down here real quick. So our Kb is going to be equal to Kw divided by Ka, or 1.0 times 10 to the negative 14 divided by our Ka, which they gave us in the problem, 4.57 times 10 to the negative 4. Okay, so our Kb so we get like 2.19 times 10 to the negative 11 as our Kb value. Now that we have our Kb value, let me just actually label it a little bit. Now that we have our Kb value, now we can solve for our equilibrium row here. So Kb is going to equal x squared over 0.067 minus x. And we're going to assume that this minus x value is small enough that we can discount it. Okay, so now we're going to solve for x. So x is going to be equal to the square root of our Kb value, 2.19 times 10 to the minus 11 times 0.067. Okay, and we get an X value here of 1.21 times 10 to the minus 6. And remember that in this case, X is going to be equal to a hydroxide ion concentration. Okay, so we can't solve for pH directly. We have to either solve for our hydrogen ion concentration first, then pH, or we can do POH and then pH. And my preference is to solve for the POH first. So I'm going to do the negative log of my OH minus. And I'm going to get 5.92. And then so for my pH, it's going to be 14 minus that. And it's going to be 8.08. So that's going to be the pH of this titration at its equivalence point. You're going to notice that the pH of a weak acid, strong base titration, the pH at equivalence point is always a little bit basic. Okay. So we have one more point that we're going to look at in this titration, and that's going to be the pH after we're 10 milliliters past the equivalence point. Okay. So get rid of this stuff that we don't need anymore. So 10 milliliters past the equivalence point means that we're going to be adding an additional amount of KOH to our equivalence volume, right? That was the equivalence volume that we calculated. So we're going to add the 10 milliliters onto that. And now we're going to look to see what the pH is going to be when we have this much KOH. We need it in terms of moles so that we can put it into the Ba table. So I'm going to take this volume and multiply it by the molarity of the KOH. Okay, and we get 0.006 moles of KOH. Okay, and now we can set up our Ba table. We have our initial amount of HNO2. We have the moles of KOH that we're adding. Okay, so our initial or before addition is going to be 0.004. And our addition in this case is going to be the 0.006. Okay. These things are going to react. And just like when we we're looking at that strong acid, strong base titration, you have to ask yourself at this point, which one is bigger? Because whatever the smaller amount is, this is the amount that's going to get used up. Okay. So I'm going to run out of my HNO2 if I'm trying to react it with all of this hydroxide. And after my titration's done, I'm going to have none left. Okay. There's still a subtractive relationship between these two though. Okay, so I'm going to put this minus over here because while these things are reacting, I'm going to be using up the hydroxide ion that I've been adding. And this is exactly how much of it I'm going to use up. So what's going to be left over would be 0.002. Okay, that's how much hydroxide ion is going to be left over. Now, when these two things are reacting, and I've used up my 0.004 moles of nitrous acid, at the same time that I'm using this up, I'm creating that much nitrite ion. Okay, so we could put an addition over here. So we end up with 0.004 moles of the nitrite ion. Now, what's interesting about this BA table, just label it, is that usually in the first examples that we looked at, when we were finished with the BA table, we had a weak acid value and a weak base value, and then we used the Henderson-Hasselbalch equation. We can't do that if we don't have a weak acid value. Okay? But what's also true is that any time we have left over strong base, it doesn't matter what the values in your weak acid or weak base column are. They're going to be completely overwhelmed by the hydroxide ion from the strong base. This is going to determine the pH almost entirely. Okay? So when you have leftover strong base in a weak acid strong base titration, that leftover strong base is going to determine the pH. If this were a weak base strong acid titration and you had leftover strong acid, that leftover strong acid would be the determining factor for your pH calculation. Okay, so I'm going to take this hydroxide ion mole value, and I'm going to find my OH minus concentration from it. So I have 0.002 moles of OH minus divided by my 30 milliliters here plus my 40 milliliters that I initially had for my nitric acid. You cannot forget to make this denominator a total volume value. Okay, so 0.04, and I'm cutting out some zeros here, but it's just for space. 0.04 liters from the HNO2 plus 0.03 liters from the KOH. So my hydroxide ion concentration is going to be 0.0286 molar. And you might be asking, like, yeah, but what about the NO2 minus here? Like, doesn't it have an effect? And it's going to still have its own equilibrium reaction with water. But the fact of the matter is that the K value for your NO2 minus or for your HNO2 is so small compared to the dissociation for a weak base that whatever the contribution of hydroxide ion is to the solution from the NO2 minus, it's going to be nothing compared to this. Like, this is just going to overwhelm it entirely. So we don't have to really, you can calculate it if you want, but the pH that you get when you add the two together is going to be minuscule difference. So there's no point in doing it. Okay. So we're going to get our POH from this value. So that's going to be 1.54. And then we'll calculate the pH from that. So it's going to be pH of 12.46. Okay, so those are all the possible points in a titration that you would need to calculate. Right, and I would recommend going back and finding another weak acid strong base titration to try, or the weak base strong acid titration, and you'll have the same kind of setup that you need that we did here. You'll use that same setup in that case. Let's move on to something a little bit different. We're going to look at some molar solubility questions. Okay, and molar solubility questions are related to your KSP expressions. Let's take a look at this. These are the questions that we're going to look at now. Okay, notice that they give you the KSP values here because to calculate the molar solubility from the KSP, you're going to need that KSP value as part of your calculation. So let's write these down. We have PbCl2 So let's take a look at how we're going to calculate these. The first thing that you want to do when you're looking to do one of these molar solubility problems is to write your dissociation reaction. Okay, so you're going to take your PbCl2. We'll start with this one. You're going to take your PbCl2 solid, and you're going to look and see how it dissolves. Okay. So it's going to form one Pb2 plus ion and two Cl minus ions. Okay. And you can write your KSP expression from that. We're going to end up using that. So we can write that our KSP is equal to the concentration of Pb2 plus times the concentration of Cl minus squared. All right, now the next step when you're doing a molar solubility is you're going to write yourself an ice table. Okay, so we can use these as our headers still, if that's all right. We can rewrite them if you want. And I'm going to have, it doesn't matter what your solid is because it's a solid. It doesn't take part in your ice table. Well, we have 0 initials, initial of the ions, and we're going to keep track of like how this would change if the solid dissolved. Okay, so this is a little bit different than our normal ice tables because in our normal ice tables we usually have something to start with. Okay, in this ice table we're not going to have any of either of the ions to start with. We're going to start with zeros for both of them, and we're going to look and we're going to see how they change. Okay, and we're going to look back at our balanced equation to really focus in on this change. The molar coefficients of this dissolution process become very important in this particular step in the ice table here. Okay, when my PbCl2 dissolves, I end up with 1 mole of lead ion and 2 moles of the chloride ion. So in my change row, I'm going to say that when my lead chloride dissolves, I'm going to end up with 1S. They use the term S to describe what's dissolved in solution. Okay, but I'm going to put the molar coefficient that's associated with the lead ion in my dissolution equation in front of the S in the change row here. I'm going to do the same thing for the chloride. When the lead chloride dissolves, I'm going to get 2 times S of my chloride. So at equilibrium, I would have S lead ions dissolved, and I would have 2S chloride ions dissolved. All right. Now, your next step in solving for the solubility is you're going to take these values and you're going to plug them in your KSP expression for their corresponding concentrations. Okay, so we can rewrite our KSP expression as S, which is going to represent our lead, times 2S, which represents our chloride ion, and we have to square that because in our KSP expression, our chloride is squared. Okay, now we know a value for this, so we can write that value out, 1.17 times 10 to the negative 5. And now we're going to simplify this set of terms. So remember that this exponent has to apply to the number and the variable. So 2 times 2 is 4, S times S is S squared. So 2S squared is going to be equal to 4S squared. 4S squared times S is going to leave you with 4S cubed. Okay. And now we're going to solve out for S. S is going to represent our solubility. Okay. So we can divide this by 4. Okay, and now we're going to take the cube root. And we're going to get a molar solubility of 1.43 times 10 to the negative 2. Okay, so the math looks a little bit different, but it's not hard. All right, so let's try it for the second compound that we have here, the iron 2 hydroxide. And we'll do the same process. We're going to start by looking at the solid, and we're going to see how it dissolves in solution. Okay, and we can write our KSP expression from there. All right, now we're going to make our little ice table up. We'll just put the ice under here this time, since we don't need to use the solid part anyway. We're really just concerned about what's happening with these ions. So we know that our initial amounts are going to be 0, and that during the dissolution process, we're going to add 1S worth of the iron ions, and we're going to add 2S worth of the hydroxide ions. And again, that comes from the coefficients that are in front of these ions. So our equilibrium row is going to be S and 2S. All right. So now we're going to do that same steps we did before. We're going to substitute in S for the Fe2+, and we're going to substitute in 2S for the OH-, and we're going to remember to square it, and we're going to remember to apply that square to both things in that parentheses. Okay, so here we have 4S. It won't always be 4S cubed, it just happened to be for both of these. The KSP value for the FeOH2 is a lot smaller. And we're going to take our cube root. And we end up with 2.30 times 10 to the negative 6 molar as our solubility for that FeOH2. All right. All right, let's look at a slightly different type of setup, but we're still going to be using molar solubility and KSP for these problems. This time, though, they're telling us the molar solubility of two different compounds, and they're asking us to calculate the KSP from that. Okay, so just kind of looking at a different angle of the same problem. So I'll just write down the info for these. Our Ag2SO4 solubility is going to be 1.4 times 10 to the negative 2 molar. Okay, I'm going to calculate KSP for both of these. You're going to see a lot of similar steps. Excuse me. You're still going to start by writing out your dissociation reaction here. Okay. So when the silver sulfate dissolves, we'll end up with 2 silver ions. We're going to end up with 1 sulfate ion. Okay, and we can write our KSP expression from this. We have Ag plus squared because there's 2 of them. Oh, that's a 2 minus. Okay, so that's going to be our KSP expression. Now we're going to use our ice table like we did before. Okay, because we're trying to set up the same scenario. We're just going to have a different unknown this time. Okay, so I'm going to set up the ice table under here again. I liked that. So here we're starting with zeros initially. When it dissolves, I'm going to end up with 2s worth of the silver ions and 1s worth of the sulfate ions. So I'm going to have 2s for my silver, s for my sulfate. So I'm going to plug 2s in here for the silver. And s in for the sulfate. Okay. So yes, I know that I just said that it wouldn't always be 4s cubed, and here it is, and it's 4s cubed again, but it just happened. Okay. So remember, when you're squaring this, it's going to be 2 times 2, which is 4, and s times s, which is s squared. Then we're multiplying it by s, which is s cubed. Now here's the difference, because in the last problem, they gave us KSP, and they asked us to solve for s. In this problem, they're giving us s, and they're asking us to solve for KSP. So we broke down the solubility relationship to its like most simplified form. Now we have to go back and we have to take this solubility value that we were given. They told us the molar solubility of the silver sulfate is this. Well, we can take that S value and we can plug it in right here. And when we solve this expression out, we'll know the KSP value. Okay? So KSP is going to be equal to 4 times 1.4 times 10 to the negative 2 cubed. Remember to follow PEMDAS when you're solving this out. Okay. And we should end up with a KSP value of 1.1 times 10 to the negative 5. Okay, you have to remember to cube this value before you multiply it by 4, or it's going to throw off your order of operations. All right, let's try one more example of this. We have our AgBr. When this dissolves, it's going to form one of each of these ions. Okay, so our KSP expression is going to be Ag plus times Br minus. Make up our ice table. Okay, zeros there. This is going to be plus 1s for the silver, plus 1s for the bromide. Okay, so we're just going to be plugging s's in here for each one of these. So we have s times s, or just s squared. Okay, so finally, we don't have a 4s cubed. But to solve it, we're going to do the same thing. We're going to substitute the molar solubility value that they gave us into our equation. We're going to solve for KSP. Okay, and we get, oops, just erase that. Negative 7 squared. Okay, so that's it. That's KSP and molar solubility. It was pretty straightforward. What makes it a little more complicated is what's called the common ion. So we're going to look at examples. We're going to look at what happens to the molar solubility when we introduce a common ion to our solution. Okay, it messes things up just a little bit. So let's look at, I'm going to put up this next example for you. So we're going to look at these two questions. So we have a CaF2 solution containing 0.1 molar NaF. Okay. The common ion situation, it's, if Le Chatelier's principle made sense to you, the common ion idea is going to make sense to you as well. You know, once we talk it out, it's kind of a logical byproduct of that. But we're going to approach it the same way as we looked at the last molar solubility problem. In terms of our initial steps, we're going to take, we're focusing on the calcium fluoride here. So we're going to start by looking at that dissolution. Okay. And we can write our KSP expression. Okay. And we're going to keep track now. So now our ice table is going to get, it's going to get a little messed up. It's not like before, because we have 0.1 molar NaF, and you have to ask yourself, well, what ions are in NaF? Well, if NaF separates, there's going to be sodium ions, and there are going to be fluoride ions. And if I have 0.1 molar NaF, that means I have 0.1 molar sodium, and I have 0.1 molar fluoride floating around in that solution as well. So when we were looking at the previous examples and we were doing our initial rows here, we didn't have anything to fill in here because we didn't have any initial components. We only had the whatever the compound was we were looking at. But in this solution, we have the CaF2 and these fluoride ions. Okay, so I didn't have any calcium ions initially, right? There's no extra source of calcium. But initially in my solution, there's 0.1 molar fluoride ions. Okay. Now, when my calcium fluoride dissolves, it's still going to dissolve the same way it did before. When this compound dissolves, it's going to dissolve and give me 1s worth of calcium ions, and it's going to give me 2s worth of fluoride ions. And at equilibrium, I'm going to have S amount of calcium ions, and I'm going to have 0.100 plus 2s worth of fluoride ions. So that's the real difference there. Now, just like in with the K values we were looking at previously in this chapter, we're going to assume that when we're adding or subtracting numbers from initial amounts, that this addition or subtraction is going to be incredibly small, and it's basically not worth us calculating it. Okay, that if we did calculate this out using the quadratic, we're going to get a number that's very close to 0.1 anyway. So we're going to assume that that is small enough that we don't have to include it in our calculation. So now instead of substituting 2s over here where my fluoride ion is, I'm going to substitute 0.1. I'm still going to substitute S in for my calcium, but I'm going to substitute 0.1 in for my fluoride. Okay? So now if I rewrite that, KSP is going to be equal to S times 0.1 squared. Okay, and I'm still trying to solve for the solubility here. Okay, so I'm gonna, they should have given the KSP value in the problem. That's not something that you'd have to know. Let's write it down up here so that you can have it for reference anyway. The KSP is 1.46 times 10 to the negative 10. Yeah, that would have been given in the problem itself. Okay, so now we can plug this in and we can solve for S. Okay, so we can write it out that S is going to be equal to KSP over 0.100 squared. And that's going to equal 1.46 times 10 to the negative 8. So that's going to be the solubility of our calcium fluoride when there's already fluoride ion present. Okay. Now, what's interesting is if you looked at calcium fluoride in water instead of in 0.1 molar sodium fluoride, the solubility of calcium in water is 3.32 times 10 to the negative 4 molar. Okay, so it is way more soluble in water than it is in the sodium fluoride solution. And that's because when you have a common ion present, it's going to reduce the solubility of the compound that you're looking at. Okay. And you can think about that, like I said, you could think back to Le Chatelier's principle. You know, your solid, your CaF2, this reaction is not going to want to shift to the right if there's already a lot of this present, right? If there's a lot of fluoride ion present, the reaction is going to want to fix that disturbance by shifting this way and staying in solid form. And that's why that solubility value gets so small. All right, let's try that second in the next example that was on that page. Okay. So this time we're going to find the molar solubility of CaF2 in 0.250 molar calcium nitrate. Okay. Again, when we have a second compound or a second component, we want to dissociate it into its ions. So we were going to be able to, that's how we're going to be able to see how it's going to affect our solubility. So calcium nitrate is going to separate into 1 calcium ion and 2 nitrate ions. So if I have 0.250 molar calcium nitrate, I'm going to have 0.250 molar calcium and 0.500 molar nitrate. But this isn't the one I'm concerned about. I need to focus in on this calcium one, because this ion is the one that's going to be common with something in the solution that I'm interested in. Okay. So I'm going to write out my separation there. Let's write out our KSP expression. Okay, and now for our ice table. Now we have something different for our initial row. We don't have any additional source for our fluoride ions, so our initial amount of fluoride 0, but we do have an additional source of our calcium ion this time. Okay. For our change row, we're going to look to see what happens specifically when the CaF2 that we're focused on dissolves. So when that dissolves, we're going to have 1s worth of calcium ion form and 2s worth of fluoride ion. So then in our E row, we're going to have 0.250 plus S, and we're going to have 2s for our fluoride. Okay. Again, we're going to assume that this S that we're adding onto the 0.250 is going to be so small that it's not going to affect our calculation. So we're going to get rid of it. And now we're going to plug in these values right in our KSP expression. Okay. So we're going to take the 0.250 that's in the calcium column, put it in there. And we're going to take the 2s in the fluoride column and put it in there. Okay. Now we're going to distribute that little exponent. So this is going to be 4s squared. So our KSP, which is 1.46 times 10 to the negative 10, is going to be equal to 0.250 times 4s squared. Okay, so now we're going to solve. I'm going to divide both sides by 4 times 0.250. No, I'm being lazy. I don't want to put it in my calculator. Okay. And I am going to get an S value of 1.21 times 10 to the -5, I believe. Yeah. Okay. So that's going to be our molar solubility of the calcium fluoride when we have a solution of 0.250 molar calcium nitrate present as well. Okay. Still well below that solubility value for the calcium fluoride when it's just in water. All right. I like that. Find the next question. So for this next question, let's talk it out. This isn't really a math question. This is more of a discussion question. This says to determine whether each compound is more soluble in an acidic solution than in a neutral solution. Okay, so what we have to understand here is that solutions that have a basic anion are going to want to react with acids. Okay, so if you have a compound that when it dissociates in solution, when one of the ions has a basic component to it, that solution is going to want to dissolve, or it's going to be more readily dissolved in acid because the basic component is going to want to dissolve, or it's going to want to react with the acidic component. Okay, so this question is asking you to basically take these three compounds, separate them into their ions, figure out which of the compounds has a basic anion, and those are going to be the compounds that would be more soluble in an acidic solution. Okay, and we'll look at that on the board in a second. For the second question, this is asking you which compound is more soluble in acid than in a base, and why is that? So this is the same type of question. It's just asking about two different compounds. Okay. So let's take a look. Have a little discussion. All right. So for part one, we've got BAF2, AgI, CaOH2. Okay, so we're going to look at the separation of each of these into their ion components. So here we have Ba2+, 2F-. Here we have Ag+, I-, Ca2+, 2OH-. Okay, now, right off the bat, without doing anything else, you should be able to look at that calcium hydroxide and say, listen, this is literally a base. A base is going to want to react with an acid. So this is definitely going to be more soluble in acidic solution than a neutral solution, because H+ and OH- is going to react and it's going to make water. Okay? Now let's look at the other two. We're going to go through that same process we talked about in the last chapter for deciding whether our ions are basic or not. Okay? The acid that's formed when a proton reacts with the fluoride ion is going to be HF. HF is a weak acid. That means that the fluoride ion is a basic anion. A basic anion is going to react more with an acidic solution than in a neutral solution. Okay, so we can give that a little check. The iodide ion would form HI. HI is a strong acid. That means that the iodide ion is neutral. So it is not going to react any more in, or it's not going to dissolve anymore in an acidic solution versus a neutral solution. Okay, but these two have basic anions, so both of these would be more soluble in an acidic solution. Okay, and it all goes back to this little equation here. That's what makes acids and bases work so nicely together. The second set of compounds they had us looking at was FeCO3 and PbR2, PbBr2. And we want to look at the same type of thing. Okay, we have Fe2 plus and CO3 2 minus, Pb2 plus and Br minus. Okay, Br minus, when it reacts with the proton, forms HBr. HBr is a strong acid. That means that Br minus is neutral. Okay, so this is already suspicious. Over here, we have the carbonate. If this reacts with the proton, it forms HCO3 minus 1. That's a weak acid. That means that the carbonate ion is a basic anion. That means that the FeCO3 will be more soluble in an acid than a base because it has a basic anion, which will want to react with that acid.